So welcome to the pre-recording of this second review in the course. It's also the last pre-recording, the last lecture in this course. The purpose is to prepare for a final exam or for the computational science prelim. So there are two main parts in this preparation. So there are these prelim questions. So a prelim happens with paper and pencil in a limited time span of 3 hours. So the first 4 questions are actually relatively short questions. On a final exam, you will have a little bit more time, and the exam is also scheduled into 2 parts in 2 ways. Either it is limited time, but then also more conceptual, or it is longer time, but then you will be expected to have to use a computer to back up your answers. So I have 8 questions prepared. So the 8 questions are just a sample on what we have covered in this course. So kind of the most important topics and concepts that one would need to remember from this course. So the final exam will happen on Wednesday, 3 May. So it is an online exam. So one of the virtues of the pandemic is that we are capable of doing everything online. To be a little bit more flexible, you have essentially 8 hours time for the take-home version or the online version, and you should definitely not need 8 hours, but that's for flexibility. So without competitions, you can sleep it over, so you have essentially then 24 more hours, so 32 hours in total, but also here again, it's for flexibility. So in this course, we covered in the very broadest sense of the word. So there are 3 different ways, 3 major different ways how to do parallel computing. We can do parallel distributed memory computing, shared memory computing, or GPU accelerated computing. On practice, through supercomputing, these 3 aspects happen concurrently in parallel, all at the same time. So in this course here, since it's only an introduction, we have not spent all that much time on really integrating the 3 ways of computing, of parallel computing. The point is, however, that what is expected is that somehow you would need what to look for when you do parallel computing. Okay, at first there are the limits on what you could expect. So here is a prelim question, a first prelim question that can be answered starting from the very early on in this course. So in one computation, we know that 1/5 of all operations must be performed sequentially. What is then the maximum speed up that can be obtained with 10 processors? This can be answered by applying Amdahl's law, and it can also be answered by a picture. So you have one timeline. So you can normalize the total sequential time is 1. You have the interval from 0, 1, cut it up into 5 pieces. The first piece is what you can done sequentially. Then the remaining part, the 0.8 part, is then divided in 10 equal segments. So the parallel time is 0.2 plus 0.08. So the maximum speed up that you can obtain asymptotically with an infinite number of processors is 5 times, so 1/5. But here you will have the speed up 1 over 2.08. And that is Amdahl's law. So in some sense, this is a very back of the envelope computation. Amdahl's law, by the way, is wrong. So as we have seen with Gustafsson. But so an alternative first question on a prelim could ask you to apply Gustafsson's law. There is also the notion of ISO efficiency that we discovered, that we treated, we didn't discover, but that we covered a little bit later in the course. That is actually a two-dimensional plot that combines kind of both Amdahl's and Gustafsson's law. So that would be a third first question on a prelim. Okay, pipelining. So pipelining is extremely useful if you have to compute many instances in what essentially looks a sequential in a sequential manner. So think of car assembly. So what is the speed up in a 4-stage pipeline? Each stage requires the same amount of processing time, so we are considering an idealized session, an idealized setting. So to process one item, it requires 4 steps. So we can take the unit time, the same processing time, the unit time. So if you have to process 10 units, it will take 40 time units. Now, if you have a 4-stage pipeline, what is the speed up? Well, the short answer is you apply the pipe time latency. So it takes 3 time units to fill up the pipeline. And after that, after you have filled up the pipeline, you can produce 1 new item per step. So in total, you will need 13 steps. So the speed up is 40 over 13. So asymptotically, again, if you have an infinite number of units, you have a plant that goes on forever, then the maximum speed up is 4. So that's the way to look at it. So I just answered this question, again, a back of the envelope computation, 40 over 13. That's the answer. What you will need to do is to justify your answer is actually to draw the space-time diagram that then also shows clearly the filling up of this pipeline and the pipeline latency. All right, so the prelim exam lasts 3 hours, so in less than 10 minutes we have done 2 questions. So if you know what we're doing, this can all happen very quickly. Tiling is a concept that we considered with shared memory parallel computing. So illustrate the importance of tiling in parallel numerical linear algebra. One of the things that we do in numerical linear algebra is solving systems of linear equation, and row reduction is one of them. Instead of doing this row by row, we will partition the matrix into blocks. So if you could see this divide and conquer. If you divide the number of rows by 2, the number of columns by 2, then you have 4 blocks or 4 tiles in your matrix. Why is that important? Well, it is important for the memory movements. Row reduction is still an operation that is cubic in the dimension, But what you should not be doing, you should not be loading in the same data many times. So we have seen the right-looking algorithm. So if you would solve, so in some sense, the other importance of tiling is that you can reformulate your row reduction of a big matrix. So this is actually what Gustafsson said. If you are considering parallel computing, work with larger computers, you have to consider larger problems. So you will consider larger problems, but with tiling you can reformulate the solving of a very large matrix in terms of the repeated solving of smaller matrices. So from a software perspective, you can apply the level 3 and the level 2 BLAS routines that are available. So you can write down a very high level, think Julia, you can write down a very high level parallel computation. Shared memory using the multi-threading that is available and the basic primitives from the basic linear algebra software collection. Okay, so but this is a prelim question, so you're not requested to do this. So the question actually goes for memory movement. So the short answer goes for right looking or left looking. But if you wouldn't think of that, you would already receive a lot of points by referring as a software developer to reusing the basic building blocks that are very well defined. What does it now mean? So you would work out your row reduction in a blocked way. Now you can do this right looking. So essentially starting from the first block, solve the first block, and then go on to the second tile on the diagonal, solve that, and then update as well. So compute the multipliers if you think about the LU decomposition. So the L contains the matrix of the multiplier. The U is the reduced upper triangular block. So you would also then do the next block. That is the right looking. And in the right looking you would, so what is important for the right looking, you would do the row reduction of everything that is on the right. So you have not now a 2 by 2, but think about a 10 by 10. So in the right looking, also in the classical row reduction, you reduce everything that is at the right of the pivot column and what is below the pivot. So that is how you would proceed. But we have covered in class that if you would do it like this, so the straightforward way, not so straightforward anymore because it is tiled, but it would still be not a very good way, because you will observe that you will load in the same right tiles all the time. So you would have a lot of movement back and forth. So the left looking way of processing the row reduction will postpone the reduction until you are currently at the diagonal. So we are proceeding along the diagonal of the blocked matrix, and we only compute what is above the diagonal and what is to the left of the block diagonal. And that will optimize the memory movements. Okay, there is, by the way, a similar question for the distributed memory, where we have the communication avoiding algorithms. All right, so I'm close to 15 minutes in, and I'm at the last question of the prelim. The last question on the prelim, so it still is organized in a way that it matches actually the original setup of the course, where we would cover GPU computing at the very end. So now GPU acceleration is part of the basic core and was already covered in the first part, also covered on the midterm exam. So the midterm exam also covers some very good prelim questions as well. Okay, what's the notion of threat divergence? So the prelim, by the way, is also a closed book. So in some sense, I do not want to trivialize the prelim. So one needs to know many, many concepts. And here I'm only hammering the most important concepts. What is threat divergence? Explain why it's a problem with GPUs. Well, the short answer is warps. So the scalable model for graphics processing units is that the threads are executed in blocks of 32. So a warp is a unit of 32 threads, and these, so it's instruction level, multi-threaded single instruction, multiple threads. Also figures out, so but the threads are scheduled in units of 32. That's the warp. So your answer should begin with this. Why is this now a problem? Well, if there is, so this still doesn't concern the divergence. Well, how would threads diverge? Well, consider a branching condition, an if-else statement. Then for the instruction level, so the alternative, so somehow in your answer the name warp needs to be in there. But you could also start out by saying that this is instruction level parallelism. And if you look at an if-else condition, so it's actually consisting of three statements. So the if test, the then part, and the else part. So these are actually three instructions. So even if you are doing the if you would see this as one computation, so the test is often very quick. But if you would do, say, a loop within the then part, then also all the other threads would actually need to do the else part. So because all the threads are operating between one unit of 32. So in some sense, one instruction then has to be processed twice. If, for example, the first half of the threads would execute the then part of the instruction, and the next half of the 32 would have to execute the second part of the instruction, the else part. So some people then say that with kernels you can't have if-elses. That is not true. So we've seen the prefix sum, where you can organize the ifs so that only half of the blocks have to go through the if part and the other half goes to the else part. So in that sense, there is no thread divergence. So thread divergence is important to keep in mind when you design kernels. But it doesn't mean that if-else statements should be avoided at all. All right, so this is the first part of this lecture, which concludes some of the concepts that were on past prelims. Let's now look at sample exam questions. Let's look at synchronized computations first. And this is a parallel distributed memory question. So we look at a very basic synchronized computation. So in the course we considered the method of Jacobi, the method of Gauss-Seidel, as two of the main examples of applications in linear algebra where synchronization is necessary. So you have a stop condition. The same happens with the computation of the largest eigenvalue of a matrix. So the largest eigenvalue then in modulus, so you could have complex eigenvalues. The power method is a very simple method that reduces everything to matrix vector computations. So in a way, this is very similar to dealing with large sparse matrices when we considered the method of Gauss-Seidel. So if the matrix has a sparse structure, then actually this matrix vector product can actually happen very efficiently. So if you describe a parallel implementation, then you think of a manager-worker paradigm. The manager will distribute the matrix among its workers. And distributing often means also that you assign to every processor a portion of the matrix that will be happening. Okay, so now there is the computation, so there are two steps essentially in there. So there is the matrix vector product, and then there is also the normalization stage. So this course follows numerical analysis. So if you would not normalize, then if the largest eigenvalue would be larger than 1, you would essentially be computing something that diverges to infinity. So the vector that you are computing is parallel to the largest to the vector that corresponds to the dominant eigenvalue. So the normalization step is important. So when you describe the parallel implementation, you have to decide on the granularity. So there is the partitioning of the matrix. And then there is also the computation of the norm. So the norm is not specified here, but you better do the one norm. We have seen the butterfly barrier. The butterfly barrier will here also do the synchronization. So the algorithm is not essentially fully specified. There is the dot, dot, dot. You have an upper bound on the number of iterations. You also have a stop test on the tolerance. So if what you are computing, so you could also keep the previous, so the formulation is with formulas. So we have an x superscript k, x superscript k plus 1. So you could, with the one norm, you could say that every processor can actually decide for itself when to stop. So there is that part of the algorithm that you have to describe as well. So the describing, let me reiterate this, in describing and answering this question, you have to do the dot, dot, dot specification. So you have to complete the algorithm a little bit. What are the stop tests? You have to describe the partitioning of the tasks, the granularity, and you have to describe the synchronizations. So what is now the relationship between the communication and the computation costs? Well, there is the startup cost, so you have to distribute the matrix among all the workers. Every worker needs to collect not only the every worker, then the communication is then the stop test, so you could use the butterfly barrier to collect the update. So every processor keeps track of the previous vector and also essentially computes how much for its part the vector has changed. So we have the forward error in numerical analysis terms. So every processor must compute its estimate for the forward error and send this back to all the other processors. So all the other processors have to decide somehow when to stop. You could also centralize this with a manager, that the manager actually says, computes the sends to every processor the termination signal. But that's a little bit more asynchronous in the data. Okay, what is the relationship between the communication and computation cost? So you have the big data at the very beginning, and also this algorithm. This algorithm has the minimum communication cost. You would hope that the matrix is structured, but anyway, the startup cost will essentially determine on the size of the matrix. If it is a big matrix, then you have a lot of data at the very beginning to distribute. But that's okay. If you do many iterations, then the communication cost will be the portion of every vector that needs to be known in the matrix vector products. Again, if it is a band matrix, you might be lucky, then the data can actually remain much more localized, because every processor would compute then only its portion of the band. But assuming a full dense matrix, every processor would need to know also assuming now that there are P processors, P workers, which would then be, it depends also here if you let the manager compute something or not. So you have the communication cost, mention the butterfly barrier. You have then it becomes logarithmic in the number of processors. As far as the scalability goes, you have the ratio between the communication cost. So this will be in every step quadratic if you are assuming a full dense matrix. So quadratic in the size of the matrix divided by P, the number of processors, the number of workers. You have the communication cost, which is linear times the logarithm of the number of processors with the butterfly barrier. So for the scalability, you have the n square computation cost and the n of the communication cost. Computation over communication. We have seen ISO efficiency. So you can do this at a purely synthetic way. So we've seen how to do this. So also on a paper and pencil version, you could draw this parabolas where there will be a sweet spot for a given number of, so you can fix the problem size, and then you can draw what is the smallest amount of processors for which you have an optimal speed up. At some point in time, if there is the ratio between size of the problem and the number of processors, at some point the computation cost has to go up. As the communication cost increases for the number of processors, and the computation cost actually goes down. So you have these typical ISO efficiency analysis that will tell you the optimal number of processors, the optimal number of the optimal size of the problem. So that is what needs to be considered in this answer. Okay, so if this is the take-home version, if you can use a computer, then you can stick with one particular configuration. So you could use MPI, either the C version, the Python wrappers, or what is available with Julia. And then the scalability will be on your computer to determine what is the observed speedups. What are the observed speedups? Okay, parallel shared memory computing. Here is the tiling again, what we have considered. But now we are interested in solving an upper triangular matrix, and we will do this with tasking. So in a way, it's an n by n matrix. So you can consider tiling, but actually, let's do this on paper. You write down the back substitution formulas and you draw the task graph. So every node in the graph corresponds to a computation what you do. So the first node that you will draw will be the computation of x4. So assuming here that the upper triangular matrix on its diagonal only contains non-zero elements. That is implicit in this question. So the first node is the computation of the diagonal of the last element in the vector x. And then the next three nodes that you can compute next to each other, this can happen concurrently, is the update of the right-hand side vector. You update the right-hand side vector with the last element. So that's the second step. In the third step, you will compute x3 and then update again in the fourth step the right-hand side. So you can see that there will be 8 steps, and that can be seen from the task graph. So for n equals 4, you could expect an upper bound of 16 steps. So you can actually, with 4, this is a really tiny example, with 4 threads, 4 tasks, you can actually do this twice as fast. So the critical path in your task graph gives you an upper bound on the maximum number of parallelism. So your critical path in this task graph, so this is fine-grained parallelism, which I would have said right from the start. We considered tiling for multi-threading and memory movements. Here actually we assume that we are at the very finest level. So the tasks are spawn, and you can spawn as many tasks as the size of your matrix. Also, this is the fine-grained parallelism. So you can actually assume now that you do have a relatively small matrix, but you can still achieve a speed up with OpenMP, for example. So the take-home version would be OpenMP usage. Or we have also seen the high-level tools in Julia to spawn tasks. Okay, generalize your observation for any n. So solving an upper triangular matrix is quadratic in the dimension. But as you can extrapolate from your example for n equals 4, the critical path has a length that is linear in the dimension. So you could actually have an n-fold theoretical speed up given sufficiently many tasks. So that's the grand conclusion of this exercise. All right, then we get to the GPU acceleration. So what is the compute to global memory access ratio? Here is a problem of evaluating a polynomial by a kernel. So the kernel, so it is doing this on a data parallel version. So we have a vector of n elements. So n should be the size of a warp, at least 32. We have a polynomial of degree d. And the algorithm that is running here is the Horner method that will execute that algorithm on the ith thread. So the ith thread evaluates the polynomial at the ith input. So this is a perfectly fine example of data parallelism. So we evaluate a polynomial at many elements. Think about finding a root finder where you would run Newton's method at many points. So we have seen early on in the course the computation of a Mandelbrot set. So this is a generalization of this. This would be one kernel that you would run. Okay, what is the compute to global memory access? So what is that again? Well, we examine the number of computations that we are doing, and you can actually forget about the loop because the loop is executed d times. So Horner's method on a polynomial of degree d requires d additions and d multiplications. So every thread does d multiplications and d additions. And if you look to the memory accesses, so it also accesses the d plus 1 coefficients of the polynomial, and then in addition of that, it does as many accesses of the input element and the output element. So you have the ith element that gets accessed in every step, and you have the of the input, and you have the yi that also gets accessed in every step. So the compute to global memory access ratio is 2 times d for the numerator. That's the number of computations we do. We consider floating point computation. So the j minus minus and the computation of the thread index, these are integers. We don't count them here. So 2 times d over 3 times d. So the compute to global memory access ratio is 2 over 3. All right. How can you save on this? Well, the x of I gets accessed every time, and that should be put into a register. So clearly. Also, the y of I. So you can already reduce significantly the global memory accesses by storing xi and yi in registers. So then you actually load in the input only once, and you save the output also only once. So this significantly reduces the denominator. So then actually you can do this with d memory accesses. So then you have a compute to global memory access of 2. You can even do better if you work with shared memory for your coefficients. So all the threads are going to load in the complete coefficient matrix, the complete coefficient of this polynomial in the instructions in shared memory. So instead that every thread loads in the entire polynomial each time when needed, there is this data parallelism of the loading in of the coefficient vector into shared memory. So in shared memory is just like registers. Then actually what you do is that if you now also work with a polynomial of degree 32 for convenience, then the loading in of the entire coefficient vector happens in one instruction. So then actually you have a constant denominator. So this, and the numerator remains 2 times d. So actually, the larger your polynomials, the better. So then the compute to global memory access increases with the degree of your polynomial. So otherwise stated is that you make from this problem a memory bound problem. So if you look at this original kernel, it's 3/2, larger than 1, memory bound for sure, although current high performance graphics cards, their memory bandwidth is also already expressed in terabytes per second. But still, the compute bound is still multiples. So you can make this problem compute bound where the compute to global memory access ratio depends on the degree of your polynomial. So as soon as your degree of the polynomial becomes sufficiently large, then this becomes a compute bound problem. So this is an important exercise that we can explain with very basic algorithms. Okay, so the last question goes into an application. So computing convolutions, many convolutions on a low number. So the alternative question would involve an FFT. But let's look at a very basic kernel to make an inner product, so to make a convolution. So this comes on the heels of thread divergence and compute to global memory access. So there is actually, so it's at some sense again, this is a very straightforward kernel. It's data parallelism. But if you look at it, so data parallelism, the kth thread computes the kth element. And at first there is nothing wrong with this, but again, coming from the previous exercise, the compute to global memory access is not good. And also the thread divergence is kind of hidden in this. So, and in some sense, if you looked at the last lecture, you know everything that is wrong with this kernel. But I will treat this now as a self-contained exercise. So the thread divergence is hidden in the sense that every thread does a different number of computations. So very bad. So this is what is wrong with this kernel. So the questions that are following here are kind of probing what is so bad on this kernel. So actually the main question on the previous slide is what is so bad on this kernel. Well, if you compute the global memory access ratio, it's the same exercise all over again. What you essentially are doing, you are updating. Every thread is updating the kth element in the output and writing it back into global memory access ratio. So again, you will have the kth thread will do a number of computations that is proportional to k, 2k, but you have 3k, so it will be 2/3 as your global memory access ratio. So use registers to accumulate. Also use registers, or even better, use shared memory. So with shared memory, all the threads are actually responsible for actually loading in the entire input. So that is reduced to one instruction. Your compute to global memory access becomes constant again. Doesn't really not depend on the degree of your truncation of your power series. Now the thread divergence is still very bad, so you can eliminate the thread divergence by pre-pending or inserting zeros. So if you look at the formula or if you look at the previous lecture, you have this k minus I sitting in there. So if you are doing that, you eliminate the thread divergence, and every thread does d steps in this loop. So there is no thread divergence there anymore as well. Okay, so this is my slide, my last slide. I went very quickly over this last exercise, but it was already presented in the previous lecture. So I hope this lecture was somehow informative. It can be seen as also the starting point to this course. So you could still look at what are the main points in this course and go back to the relevant lectures where we explained and introduced the concepts more carefully.